Okay, so by the way, the assignment number 3, there are a couple questions on observer design, and this year I'm kind of running a little bit, a couple lectures slower than previous year. So the assignment, once we finish this week lecture, then you'll be able to finish the assignments. Okay? Yeah. Okay, so we'll talk about a new topic today, which is an observer. Let's look at the idea of observer first. Okay, and then we'll specifically look at two different types of observers. One is called the full order observer, and the other is called reduced order observer. Okay. All right. So let's start from our original discrete state space model. Okay, so this is a typical state space model. I'm using a single input, single output as an illustration right here. Okay, yeah. Now, from this model, just recap the meaning here. X of t is a state variable, u is your control input, and y is the output of the system, right? So this is the very straightforward definitions. And based on the state space model, we can use, for example, pole placement. Okay. The idea of pole placement basically is you generate your control input, okay, based on the negative feedback of the state variables x and times a gain matrix k. So that gives you a control feedback at here, right? Now, if you look at this pole placement simple design, and there are a couple issues at here actually. Okay, first of all, there's an assumption for the pole placement. The assumption is you're using this gain k, which you offline calculated, right, based on certain poles, and then times what? Times the state variables x, right? So to generate the control input. So basically means you're here. The assumption here is this x of a k, right, is available. That's assumption. If it's not available, then you can multiply that x of k with k, right? Yeah. So that basically is the idea here. It's available. Okay. And in a lot of cases, for example, in our case, your x of k in a project, it could be theta dot, not dot. So write it on a position and velocity, right? So your state variable is position velocity defined as this, and you do have sensors to measure the position and velocity. So they are available, right? That's fine. So this is fine in here. Okay. However, not all the time that the state vectors or state variables are available. For example, what if you only have a position sensor but no velocity sensor? Right. So then basically you don't have a direct measurement of the position signal at here. Then that basically means this state variable or state vector at here, they're not completely available, right? Not completely available. Okay. If they're not completely available, then what do we do? Then we cannot just use this mathematical formula, use negative k times that, because, for example, this one's not available, right? So that's the objective what we're trying to deal with at here. Okay. Available. Here, by available, we mean basically measurable, okay? Yeah. So basically means you have a sensor, or somehow you can basically measure to give you this quantity, okay? The value of that. So the idea basically, if not all x of k, okay, is measurable, okay, So then what to do, right? So that's the point here, okay? Yeah. So what we want to do is, the objective is, okay, is to design a so-called observer, and sometimes we also call it estimator, okay, to obtain the non-measurable state variables. So that's the idea. Somehow if we can design an estimator observer, right, to give us the estimated quantity for the non-measurable ones. So let's say you have a position and you have a velocity. So you have a sensor measuring position, but you don't have a sensor directly measuring the velocity, right? So then, can we come up with an observer that designed based on available ones, then measuring or estimating this unmeasurable state variable velocity at here? Okay. So I'll show you a diagram in here. That's the idea of how observer works. So let's say we have a system in here. And you give a system control input, and system has output y of k at here. Okay. So if you look at this box right here, right? And for this box, if you look at the outside the box here, basically control input, that one you have it, right? Because you know, this is what you give it to the system, so you have this information. Output of the system, that you also have it, so that's the actual output of the system. Basically, if you look at the output of the system, which is over here, right? And the C maybe is a 0, C maybe is 1, 0, and times x1, x2. So you're taking only the x1, which basically means your output is this x1 here. That's your actual output, okay, which has a sensor measuring it. So both of this, from this diagram here, both of these are available at here. And then we design, well, our idea is we design an observer at here, okay? So we'll look at how we can design this box. The observer will take whatever available information. Okay? So it takes the available control input, it takes available the system output. Okay? So that's your observer here. Yeah. And the observer, based on certain mathematical algorithm, it will try to spit out an estimated state variable x of k. So this x of k at here, this is basically called estimated x of k. Okay. So that's not an accurate description, it's estimated, but if your observer designed appropriately, this x hat of k will eventually be the same as the actual x of k. Okay, yeah. So idea is that the x of k will go to x of k as k goes to infinite. Okay. So this estimated x of k here, x hat k. Now this is the one we will make use of to generate our control input here, right? So then you can apply a negative feedback gain in here, and then coming back to this loop. So that is basically the new structure here, right? Previously, if you recall, the u basically directly is negative k times whatever the system x of k is. Now this is negative k times the x hat of k. Okay, yeah. So that's the structure of the observer, huh? The question here is, of course, we're going to design this observer here, and then we'll present the two different types of design. Okay. Yeah. For now, the design is based on the system with a clean signal, no noise. And later, we're going to extend this further. So, what if there's noise in the system? We also want to design an observer. So that's where the next step, okay, called a common filter, comes to picture. Okay. Yeah. Okay. So let's look at basically a little bit more formal definition at here. Okay. Basically. again, given this one here, is basically what we want to do is to generate this x hat of k, okay, this x hat of k, based on what, right? You look at this diagram here. Based on not just the current y of k, u of k here, okay? It's actually based on basically y of k minus 1, okay, and up to y of k minus n plus 1, basically n steps, okay? And also the control signal in here includes the past control signal. Okay. So that's the idea, huh? You need to make use all available information to generate the estimation of x of k here. And before we move on, we need to have a theorem, just like the theorem for arbitrary pole placement. Here we need a theorem basically for doing arbitrary observer design. Okay. The necessary and sufficient condition for state observation. Okay. So under what type of condition, necessary and sufficient condition, you can design a state observation, or you can realize a state observation. And this condition is that basically observable condition, which is you look at the rank of this matrix and its rank needs to be full rank n at here. Okay? If you satisfy this condition, then what we see is that the system is completely observable. It's completely observable. Yeah, so basically if you want to design an observer, first step is to check the observability matrix rank. If it's a full rank, then you go ahead and you design. If it's not a full rank, then you don't bother to go ahead designing, right? Yeah. Okay, so let's look at the first one. I'm going to look at, as I said, I will look at two different types. We'll look at the full order. We'll also look at the so-called reduced order. Okay, so that's the two types we're going to look at. Okay. The first type, we'll look at this full order observer. Full order observer here. Full order observer is the simplest type. Okay, but before we formally introduce the full order observer, let's look at basically back to this diagram here. Remember, this is the block that we're trying to come up with at here. Okay, and the system is our that system, which is this one here. Right, this is our system. Okay, okay. We're basically trying to realize this observation or estimation using the mathematical model here. Okay, so let's think about let's basically consider first. Let's consider the following observer model. Okay, so I'll write it down, the observer model here, x hat Okay, here is a so-called observer model here. Okay, so look at this mathematical equation. Essentially, the symbol-wise, remember we use x hat representing the estimated quantity for the state vector x. Okay, yeah. So x hat is estimated x. Okay. So why this model work, and why, or maybe shouldn't say why it works. Okay, how this one can be observer model here. The reason is because if you look back, okay, the system. This is our system, right? This is our system here. Okay, and the system is what you basically presumed or based on certain rigorous derivations. You see, okay, here's my system, linear with this matrix A and B, so you're pretty confident this is our system here, right? Yeah. And then the observer basically is recycling. This observer here is recycling the idea of the system that you have derived or you have come up with. So you see, okay, so I'm not going to really come up with a brand new mathematical model. Then why don't we just use the original system matrix G and H instead of basically the actual state. Now we use X hat. Right? That's the difference, right? That's a natural. Actually, that's a natural basically a reaction for people. You're not going to come with a brand new model. You're just recycling your original system model here. Okay. Yeah. However, you will see there is a little bit problem in here, right? So I'm going to call this is 1, this is 2 equation, okay? And then, so maybe let me just write down the original system here. So original system let's call it 3 and 4. So immediately from here, you also need to bear in mind the objective, right? The objective is you want your x of k, okay, to be the same as x of k as k goes to infinite. Okay, so based on this observer model and the actual system model at here, so I'm going to do a little bit of manipulation at here. Okay. And we'll use number 1 minus number 3. Okay, so use number 1 minus number 3. That gives us x hat k plus 1 minus x k plus 1 equal to g times x hat minus x plus h. Well, it's not plus h anymore, because when you use 1 minus 3, these two terms, they cancel each other, right? They got deleted to each other, on each other. Okay, so this is basically a new equation. Then we'll define our left side and also the right side here. So we call it error. So this one here, we'll call it error k plus 1. And here is the error k. So that's the error basically is the difference between the actual state value and the estimated state value here, right? So that's the error. Okay. So idea is you want the error to go to 0, right? If the error goes to 0, then you get a good estimation x of the actual state variable. Okay. Yeah. So let's see. I'm going to write down here. So this e at here is estimation error. Okay, estimation error here. So ultimately, this is in short, you get error difference equation for the error at here, which is e k plus 1 equal to g times e of k. Okay, that's the error. Okay. So I think we actually have seen similar stuff at here. So if I do an iterative basically step at here, so basically let's say start from the first one, you get, okay, starting from initial value here, right? Starting from initial z of 0, and then you get this one here, right? Yeah. And if you keep going, okay, and you get what? E of k equal to, okay, g to the power of k and e of 0. Okay. So that's the solution basically. This is the solution here. That's a solution for this difference equation, right? Okay. Yeah. So if you look at this solution at here, and I think we have seen similar solution, right, when we deal with the pole placement. under what condition, right? Under what condition that this E of k will actually go to 0, right? So here, right? The question is, under what condition this E of k will go to 0 as k goes to infinite? Pardon me? Yeah, Simon first.
G has to have poles that are smaller than G.
That's right? The G is a matrix. If a G is just a single value, then the G has to be a value less than, absolute value has to be less than 1, right? So G is a matrix, then G's eigenvalue needs to be within unit circle, right, in order for G of k to go to 0 as k goes to infinite. Okay? Yeah. So this condition basically, G's eigenvalue need to be within unit circle. Okay. So that's the idea, right? And that's the condition that will make sure that E of k go to 0 as k goes to infinite. But this is kind of ideal, isn't it? So G is a system matrix. You cannot guarantee that the system matrix G will always have eigenvalues to be within the unit circle. So that's not a guarantee, right? It's not a guarantee. If you're lucky, then fine, right? This will work. But what if the system, the eigenvalues are not within unit circle, right? So basically what this means, this observer model at here, okay, it could work, but it doesn't work all the time, right? Yeah. So that's the point at here. We need to make a little modification to this observer at here to give us the freedom, so we can basically design to satisfy all different type of situations, right? Yeah. Okay. So basically, bear in mind of this the motivation at here. So what if G is not stable, right? Basically, if you have a poles outside the unit circle, that means G is not stable. Okay, so now what we can do is, okay, if you look at it, this observer design at here, okay, this observer, it didn't really take into account of the system output. Here's a system output here. Okay, the system output, okay, is available. Okay, remember this is basically this is a fact. When you have a sensor, you can take certain output, right, out of the system here. So now, okay, we modify. So now we're going to modify the observer model. Okay. So how do we modify? Here is the way we modify the following here. Okay. X hat k plus 1, okay, equal to G x hat of k and plus H u of k. Okay, so that's exactly the same as the observer right now, right? And now we introduce, okay, an additional term at here. I'll use the red color, L times y of k minus y hat of k. Okay. That's the modification at here. Okay, that's the modification. Basically, the red part, okay, is what we are added at here to modify the regional observer model. And let's take a look at this modification, whether it makes sense or not. Okay. So first of all, the L at here is called observer gain. Okay, this is observer gain. If I look at the dimension of this expression, right? So x hat is a n by 1 vector at here. This is n by 1, and over here, this y at here, this is system outputs, right? So this is basically the known quantity at here. And this y hat set here, that's basically your c times x hat of k. Okay, c times x hat. You can call it estimated output, right? Not the estimated variable. Okay, estimated state variable is this one. And L at here is observer again. In order for the dimension to match, the L needs to be an n by 1 vector at here. Okay, so then you'll be able to create n by 1 vector, so the same dimension as your x hat. Okay. Is that good? Okay. So everything else basically is based on this observer, this modified observer here. Okay. This is essentially called a Bloomberg type of observer. Okay. So let's look at this observer now. I'm going to modify it, just rewrite this a little bit here. Okay. Just rewrite it. So how do I rewrite it this? We're gonna multiply the L into this bracket. So you have L times y of k, L times y hat of k, and y hat of k is cx hat of k. So basically multiply L, you get L times c times x hat of k, right? Okay, and you got a gx hat of k here. So group these two similar terms. So what do we have? We get g minus L times c x hat of k, right? Yeah. And h of u k, just leave it there. And then you have L times y of k. And L times y of k is L times c times x of k. Right? So that's the modification, right? No change, just the one step of simplification. Okay. So the reason we're doing this one here, if you notice this, basically you have x hat k plus 1, you have x hat of k, okay, and then you have a rest of the term in here. Okay, so overall, this is like our state equation format, right? State equation. What's a state equation format? It's x. This is k plus 1 term, and then g times this, and then plus another term in here, right? Yeah. So overall, this is in that format. Huh? Yeah. Just a couple of quick comments in here. Huh? This is what we call, it's called a prediction type observer. A prediction type observer. Why prediction type observer? Is you can see that your x hat k plus 1 basically is the next step, right? It's the next step. The next step prediction, it's based on the previous and the previous set here, right? So that's, you're using all the past information to make a prediction for the next one here. That's called a prediction. Okay. And second of all, okay, there's this G minus LC at here. Okay, as we're going to see, this G minus LC, this is called the system, okay, matrix, okay, for observer. Okay, for the observer at here. And it's very much the same idea as the system matrix when you design pole placement, right? When you design pole placement, U equal to negative kx, and you get a feedback, the system matrix becomes G minus HK, right? KH, right? HK, G minus HK, right? So that's the connection in here.
Is there an acronym formula type for observer?
Yes, there will be. Yeah. So to calculate L, right? Yes. That's the idea. We're going to come up with a formula for calculating the L at it here. Okay. Yeah. Okay. Good. So from here, let's move on at here. Okay. Now I'm going to basically use our objective is to look at the error dynamics. Okay. The error dynamics, and the error is the estimation error we're talking about. Okay, so this time I'm going to define this, and actually same thing, but let's use x of k plus 1 minus x hat here, okay? Aerodynamics. So if this is aerodynamics, then naturally you bump up one. Sorry, what's going on here? You bump up one step. Okay. So this is your k plus 1 steps here. K plus 1 step. Okay. Okay. So let's define this is equation number. Let's define this is equation number 5. Okay, so this is equation number 5 in here. Okay. And we define equation number 3 up over there. So equation number 3 is your original system state equation. Okay. And this is your equation number 5 over here. Okay. So now let's use equation 3 minus equation 5. Okay, equation 3 minus equation 5. So you can take a look at the minus equation 3 minus equation 5, right? Equation 3 is over here. Okay. So left side minus left side and right side minus the right side. So you got h of u of k cancel out, right? So let me rewrite this one here, okay? Yeah. So we got e of k plus 1. Okay, so basically over here this is the e, and the other side this is equation 3, this is equation 5, right? So equation 3 minus equation 5 would give us g times x of k plus h u of k. That's equation 3. Okay. And then minus g minus lc x hat minus h u of k, and then minus lc x of k. Good. So that's the right side. For the right side here, this is the results of 3 minus 5, right? So 3 minus 5. Okay, so you got this term and this term cancel out. And then for g of x of k here is xc x of k here. So what do we get? We get a g minus lc. Group these two terms, x of k. Then minus g minus lc again, x hat of k, right? Yeah. And then you got it. Yeah, you got the same common factor right here, x of k minus x hat of k. Okay, so and x of k minus x of k is the definition for what? The error, right? So this is g minus lc error k here, and this side is error k minus k plus k. Okay, so you see that type of observer results in the aerodynamics, estimation aerodynamics with this relationship. So now you immediately can see what's the difference between this aerodynamics and the previous aerodynamics. Previous one is just simply e equal to e k plus 1 equal to g times this. That's it, right? But this time you got a g minus lc here. Okay? Yeah. The difference is the L is a choice of the user, right? You define the L here. So that's a degree of freedom. That's what we still call the design, right? So you design the L to be whatever it is, which will define the response or the dynamics for the error here. Okay? So there we go. So the idea here is very much the same as previous pole placement now, right? So what we want to do is we want to choose L, okay, such that this g minus lc, okay, its eigenvalue. Okay, so the g minus lc's matrix eigenvalue are within unit circle. So if you can achieve this simple objective, okay, so that then you get basically you'll get e of k go to 0, as k goes to infinite. As k goes to infinite. So choosing the L appropriately, right? To be within unit circle, that's the first requirement. However, you do need to choose the L, not arbitrary choice of L, right? We do need to choose it actually wisely and appropriately here, because as you can see now, the choice of L, okay, the choice of L, it determines the aerodynamics. Okay. I should say estimation aerodynamics. Okay. Just like you choose the pole placement gain K, which will determine the system response dynamics, right? Yeah. And here you choose the L wisely, okay, and then you determine the aerodynamics. Okay. And the next comment here is basically we need to choose the L, okay, by considering this feedback gain K at the same time. So the point basically is your gain of K is coming from here, right? So U of K equal to negative K times, in this case, it's negative K times X hat of K, right? That's your feedback, how you generate your control input. And this K is determined by the choice of the desired poles, right? By where you want to place the poles there. And this K will decide on how the system output will behave according to your user specification, right? Certain settling time and a certain damping ratios, stuff like that. Okay. Yeah. So when you choose the L at here, what you want is, okay, remember this rule at here. You want your observer poles. So basically, you choose the L. It will decide on the eigenvalue, which is the pole. The eigenvalues for the G minus LC. So we want to choose our observer poles, okay, to be 2 to 3 times faster than system poles, okay, than the closed loop system poles. So you essentially you have a G minus LC, you have a G minus HK, right? So here you have this is basically called observer pole, and here you have your closed loop system pole, right? And you want the observer pole to be faster than the system pole right here. That kind of makes sense, right? Because why? Because if your observer is not good enough, and your control inputs generated based on the observed value will not be good, right? So what you want is you want your observer to behave a little bit faster to catch up the actual state variable value, and then your control input will be able to follow that actual measurement or actual estimation correctly. Okay, yeah. So that's why we wanted this observer poles, okay, to design to be faster than the system poles here. Okay. Okay. So now the last part of the question, and here for this full order observer is, how do we calculate this L at here, right? How do we calculate the L to come up with a certain observer poles? So we're not going to derive actually the calculation. We're going to use a little bit knowledge we learned for the pole placement calculation for this K at here to calculate our L at here. Okay. Yeah. What we're going to come up with very similar. We're going to come up with a formula so-called Ackermann's formula. Okay, so we're going to come with the Ackermann's formula for this L at here. Okay. First of all, okay, recall this pole placement. And the Ackermann formula for pole placement is what? Is 0, 0, 0, 1, H, GH, G minus 1, H, negative 1, alpha CG. That's Ackermann formula for calculating the feedback gain K, capital K. Okay? G is a system matrix, H is a system matrix, and alpha CG at here. Okay? Alpha C, first of all, alpha C of Z, okay, is equal to the Z to the power of N plus alpha 1, Z to the power of N minus 1, and up to alpha N minus 1 Z. Plus alpha n. This is the desired polynomial, desired characteristics equation, right, for the closed loop system. So this is the so-called desired closed loop characteristic equation. Okay. And where is the desire from? It's from your choice of closed loop poles, right? You know, if you have a second order system, you pick 2 poles, then you can calculate this desired closed loop characteristic equation easily, right? So replace the Z with G, and that's your alpha CG. Okay, so that's the Ackermann formula for the feedback gain K, right? So we're going to try to make use of the results that are here. Okay, and if you recall again, this is based on G minus HK, right? This is G minus HK. When you have a feedback system, G minus HK, here's how your K is calculated. Okay, so for observer, okay, the observer that we designed there. Okay, first of all, okay, we're going to have a very similarly. We're going to define another polynomial called alpha EZ. Okay. So alpha EZ is basically the desired closed loop observer characteristic equation. Okay, so I'm going to define this as alpha E1, alpha E, call this n minus 1, and alpha En. So this one is called desired observer characteristic equation. Okay. Right, so this alpha C, right? That's G minus, not the G minus, no, it's Z I minus G minus HK. Okay. That's the desired closed loop, and this is the desired observer. So whatever your L is choosing, you pick a pole. A pole here, we'll look at example later, okay? And then you can come up with a desired polynomial here based on the choice of L. Okay? Okay. So let's do a little bit comparison, right? So here, this side here is a G minus LC. This side here is a G minus HK. So observer, you got a G minus LC here. Feedback pole placement, you got a G minus HK here. Now remember, this is different, right? See here, this is L is the design parameter, and K is design parameter. So unfortunately, what happens is this is not a G minus CL. If this is G minus CL, it will be in the same format as G minus HK, isn't it, right? So then probably I can just replace a couple of parameters to use that. So this is basically different. But what I'm going to do is I'm going to do a transpose of this side here. Okay, so let's take a look at what does this transpose of this equal to. Transpose equal to the G transpose minus LC transpose, and LC transpose equal to C transpose L transpose, right? So now I can compare these two now. Okay. So now you see the design parameter is same as this design parameter. It's all on the left side of this C, and this is on the left side of H here, right? Yeah. So based on these two comparisons here, and your calculation of K is this formula, right? It's this formula here. So I'm going to do a little bit mapping out of here. I'll see the G transpose map to this G out of here, and the C transpose map to which one? H. And then the L transpose map to this K out of here, right? So if you do a little bit apple and apple comparison, it's not a completely the same apple, but G transpose to G, C transpose to H, the L transpose to the K, right? Yeah. So finally, you see, I'm trying to if I'm using this formula at here, so that K will be replaced with L transpose 0, 0, 0, 1. Okay. So no change over here. And H, you replace that with C transpose. And G, you replace with the G transpose. So the first here is H, so replace the C transpose. G replaced with the G transpose. H is C transpose. And up to G transpose to the power n minus 1, and C transpose inverse. Finally, alpha E is a G transpose. Okay. So that's the formula, right? This is basically still Ackermann formula. This is the Ackermann formula for, not for L, for what? For the L transpose, right? And after this step, you do one more transpose, you get your L. Okay? Yeah. So that's the point of calculation for the L at here. Okay, for the L. Yeah. Now, if I use MATLAB, right? Basically, if I use MATLAB to help me calculate, and what we do is we use the Ackermann formula. So ACKER. Okay, ACKER is Ackermann formula, and what you give to the Ackermann formula is G transpose, C transpose, and then a vector, that's whatever you want to call it. So this vector POB here, this is a vector for desired observer pose. Okay, desired observer pose. So it's a column vector. Basically, let's say the first one maybe 0.3 plus J 0.3, second one 0.3 minus J 0.3, for example, right? Yeah. So that's your observer pose. If it's 2 by 2 system, you plug it here. G transpose, C transpose. Now the return of this one here, it's not L, it's the L transpose, right? The L transpose. So then you need to do another transpose, the final results to get your L. Is that good? Yeah. If you do hand calculation, then of course this is your formula for hand calculating L transpose. Okay. But you can linear algebra, operation. You can further simplify that because we know that L is L transpose. Let's say L equal to transpose of this, right? So L equal to transpose, or L is the transpose of all the left sided here. Okay, that seems to be too much, but it's actually not too bad. There is a formula here. When you have A times B times C transpose, and that equal to C transpose, B transpose, A transpose. Okay. So if you look at the Ackermann formula, the L transpose equal to what? A times B times C, right? So there are basically three big matrices at here. So A times B times C. So all you need to do for hand calculation, so L transpose, and you get basically C transpose, right? C transpose here. And the C transpose is actually equal to alpha E and G. Okay. So originally you have a G transpose, and the C transpose just become alpha E and G in here. And B transpose is the transpose of the middle matrix. Okay? This is the row matrix at here, and that row matrix become a column matrix, right? At the same time, you do a transpose for each individual element. Okay, so that will become the B matrix. And then A matrix becomes a column matrix, column vector here. Okay, so this is your L here, okay? The actual formulation for L. If you are required to hand calculate it, then you can use this formula to hand calculate the L at here. Okay? Yeah. Okay, so let me show you an example at here. Yeah. Nope. Okay, so let's look at the double integrator as an example here. And this is one of the midterm exams question. Here's the double integral, right? And that can be a simple representation of a system, mechanical system, inertia with input of torque. Then you have a certain rotation, right? Okay. We can linearize this system, and the results of the linearized system is that's the results of this linearized or discretized system, not linearized, discretized. And the x of k here, basically the first one position, the second one is a velocity, right? That's two state vectors, two state variables. Oh, and then by the way, you can just remind me here for the midterm, there's a lot of quite a few of us making a mistake at here. When you do the discretization, you have this formula, right? The matrix A equal to e to the power ft, or e to the power gt, where f is a continuous system state matrix, right? But when you calculate, you calculate this e to the power ft first, right? Equal to the inverse Laplace and si minus f at here, and then right, the inverse at here, I think, right? Yeah. Now a lot of you making mistakes is this. So you see, okay, so e to the power ft equal to the inverse of this, right? But that doesn't equal to this. Okay, you have to calculate this one first, and then replace the small t with the sampling time capital T, right? The problem is some of you, when you do this step here, you're assuming basically this equal to this. When you do the inverse Laplace transform, and some of you here, it's supposed to be a t at here, right? The t comes from inverse Laplace of 1 over s squared. Okay? But then you look at your Laplace of the table, instead of using t, and then you said, okay, kt, right? Because the small t after sampling is k times capital T, right? So that's a mistake. Then you basically say, okay, so a equal to this whole chunk. And there's 1 in here, 1 in here, kt, right? So that once you get this wrong, and then the rest will be wrong, right? So make sure the definition of this a at here be properly understood. Okay. Yeah. Okay, so let's go back to this question, okay, observer design. So what we're going to design here is we're going to design, of course, observer, and also ideally we need to design a feedback system in here, right? Yeah. So first of all, let's say I'll skip a few steps here. Let's say you design a feedback system, and the feedback system is designed as u equal to negative k times x hat. Okay, yeah. I think we did one example in previous step. So k, okay, in the previous example, k is obtained from a desired pose, and we use the pose 0.5 plus minus 0.5. Right? Yeah. So you can design your k as completely separate step process from this observer by picking an appropriate pair of pose and here. So you can pick this one here using Ackermann formula. You'll get your k matrix, right? Yeah. Now step 2, if let's say in this question, let's say if I don't have the measurement of the velocity here, okay, don't have the measurement velocity, then we design observer. So for observer, okay, and we need to pick a pole location for the observer, right? Let's say now we pick So what we want to pick is we want to pick the so-called deadbeat response for observer. Okay. Deadbeat response for observer. Now, if you remember deadbeat response, we have a deadbeat response for designing K, right? What does deadbeat response means in terms of the pole location? At 0, right? So essentially, for observer, we want to place the pose for the observer at 0 location. So if you look at observer equation here, this is your desired polynomial, right, for the observer, which is this one here, okay, which is this. And if you pick pose all at 0, then the desired observer polynomial is going to be z to the power of 2 plus 0 for the rest of the term here, right? So that means in this case, if I decided for deadbeat response for observer, then the alpha e is just z to the power of 2 now, okay? That desired polynomial for the observer. It's basically z minus n times z minus 0 times z minus 0 because z squared. Okay, so now I'm going to make use of the formula that I just derived for L calculation. L equal to alpha E of G, and then Cg at here, 0, 1, and here, right? And then you have your C, you have your G, okay? And alpha E of Z is G, just G squared at here. So if you plug in everything, you get 2 over 1 over t. So 2, that's right, 2, it's a vector, 2 and 1 over t. That's your L observer gain matrix at here. Okay. So, and I want you to practice, okay, yourself, okay? Let's say if I assign the observer pose at 0.3 plus minus 0.5, and this L, what does that equal to? Yeah. Now, why I choose 0.3 plus minus 0.5? Remember, we want our observer pose to be faster than the feedback system pose, right? So feedback system, in this case, let's view design your K as 0.5. Then if I want it to be faster, then at least this R value needs to be smaller, right? So I just shrink that real part from 0.5 to 0.3. Okay, but you can choose arbitrary any other values here. Okay, so I'll show you the simulation at here, though. Okay. Yeah. Over. Okay. I have two different type of. It's the same design, but it's two different type of parameter initialization at here. Okay. So let me open the other one here. So both of them have been uploaded to the. Yeah. So if you look at the two diagrams, initially you actually don't see any difference. So these two diagrams are the same thing. Okay. But let me explain. So the top portion is our system, right? This is a GH, our original system at here, and the bottom portion, this is the observer at here. Okay, yeah. So the k times estimation at here, okay, and observer gain is L over here, right? Yeah. So let's see which one is. If you double click on the L, for example, right? So I have a 1 over T, that's the calculated deadbeat observer value. Okay. You do need to basically, in this case, you do need to plug, type the T value first, right, before you run the Simulink. Okay. The other one, what I did is, okay, this is actually, I will come back to this again. There's another way to initialize in the formula in the MATLAB. You click on the view, okay, and you go to Models Explorer, and you go to Model Space, Model Workspace. Okay. So you can initialize the system parameter over here. Okay, so you can type your code at here to initialize the system. So for example, I initialize my sampling time to be 0.5 at here. Okay, yeah. The advantage for doing this is basically every time when you open up the Simulink model, then you don't have to worry about some initialization anymore. Because once you open this simulation model, if you whatever here will be automatically loaded and initialized, right? So that's the advantage for this type of design realization here. Yes.
In one of these sample questions, you asked us to run the observer manually.
Yeah.
We just need added values in the middle.
That's right. Yeah, you need to edit the G matrix, right? You need to add it to the H matrix, of course, okay? And you also need to calculate the K, the L for that system, yeah. But the structure is the same thing. So if I ran it, so let's take a look at it, okay? This is the response set here. The scope takes the system output and also the observer's output. Essentially, it's a comparison between x1 of k and x1 hat, right? So the position estimation. Ironic, actually, you don't need to. Position is variable in this case. ideal is to take a look at the velocity comparison, right? Yeah. So if you see the blue color, I believe is the system actual output state. The yellow color. The blue color is the observer output. And as you can see, the errors between the observation and the actual will automatically go to 0 as the k goes to infinite, right? Yeah. So you can modify the c. You can actually modify the c value here. You know, instead of 1 0, you modify to 0 1. Then you can take a look at the estimation of the other state, right? The other state here, okay? Or you can output everything to one step right here, okay? Yeah. So anyway, so that is the observer design. This is basically full order observer design right here. Okay. Yeah. Any questions? All good. Yeah. And you can implement this observer on the actual system. Okay. And then you can combine this observer here. I think it is already combined because I have the calculation in the gain matrix at here, right? Yeah. So there is control in the system. Okay. Okay. So let's do a little bit of time here. There's one more topic. Basically, is the so-called another type of observer under full order. So called the current observer. Now this one, I would say is probably, let's just make it an optional here. I'm not going to test you this current observer in the final exam. Okay. But you can very well implement in the simulation or in project for sure. Okay, but this is not going to be tested in the final exam. But you have one assignment, I think you can practice. So current type of observer is basically what we do is we make use of this y of k. Okay, make use of the output y of k at here. So what it means is I'll write down the model here and we'll show you basically what I mean by make use of this. Here is the current observer model. Okay. It has two steps. The first step is doing this. Z of k plus 1 equal to g x hat of k plus h u of k. Okay. This is a step 1 at here. Okay. The step 1, if you look at the step 1 here, it's basically, especially look at the right side here. That's like the simplest, the full order observer model I started with, right? You know, gx hat plus hu of k. That's the simplest type, isn't it, right? You know, but it's basically I changed the variable name from x hat to z. Okay, yeah. So this one here, what we call that is the prediction. Okay, this is a prediction in here, and this is z of k plus 1 is prediction of x of k plus 1. Okay, that's prediction. Now the second step is to come up with the actual estimation x hat. So what we do is we make use of this z value, which is the prediction from the step number 1, and then we modify this, okay, by adding this term in here. Like this. So that's basically, as later when we learn common filter, you actually will have a very similar structure as this one here. So this is a step 2. Okay. It's like step 1 is not so accurate. Then you do the step 2 to improve the accuracy of the results from the step 1. Okay. So that's step 2, and can you call that improvement? Okay, improvement here. But the improvement, if you look at the improvement here, so this is your x hat of k plus 1, right? This is based on your prediction and also based on what? Based on the y of k plus 1. And y of k plus 1, the index is the same index as this k plus 1 at here. Okay? So that's where the current observer, the name, comes from. So your estimation at here are actually based on the current information, y of k plus 1 at here. Okay? Yeah. And based on this model here, we can do a very similar approach to derive the aerodynamics. Very similar approach for the aerodynamics at here, like the steps that we have just gone through. Okay. And here basically is, if I call this is equation, let's say this is equation number 6, right? So if you recall that this first term is equation number 3, okay? So we're essentially using equation number 3 minus equation number 6, which is this term right here, okay? Yeah. Equation 3 minus equation 6. And if you do that, okay, and I'll simplify myself a little bit. You can take a look at. You'll be able to get the following relationship. All right. So if you use equation 3 minus equation 6, and you'll get aerodynamics, which is this one here. Okay, which is this one. And this is slightly different, right? This is slightly different here. You know, basically, if you look at the results for the full order we just derived here, what was that aerodynamics? G minus LC, right? And here is G minus LCG, okay? G minus LCG, okay? So in terms of the formula, it's not much difference, right? So you can consider this CG to be the C at here, okay? So all you need to do is what? You need to just replace the C at here with CG. Okay? Replace the C with the CG here, then you get this calculation for the L at here. So basically C and the CG at here is a mapping. Okay? The C and the CG. And then the L, okay, is alpha E and G. Okay? So then CG at here, CG square, CG to the power of n inverse 0, 0, 1. Okay. So that's the L matrix. Okay, if you design this so-called current type of observer, okay, current type of observer. Okay, so. Calculation-wise, it's not too bad, and you can certainly basically plug in the matrix values and then calculate the L. Okay, yeah. So that's all about full order observer design. Okay. Any questions? Yes.
Just for that formula, can we also pull the G out and just do like I minus LC2, just don't do the extra matrix coverage?
Take.
G plus 1 or G minus LCG.
Oh, you mean pull this G out?
Yeah.
If you pull it out, you could, but yeah, here you could, but ultimately when you try to use the right, yeah, you had pretty bad, right? Yeah, because it's a comparison between this one and this one here, right? Yeah, yeah.
For the projects,
yeah.
You have like 5 or 6, it looks like, different controllers.
Yeah.
Should we develop the theory for all of them before going to test any of them?
You should develop the simulation before going and implement. Yeah.
Is there any, because I know we've done Kalman in other courses.
Yeah.
I'm not sure what some of the, like the LQR and the LQG.
Yeah.
Is there documentation you're able to post specific to those so that we can get to the simulation?
Yeah, after finish the observer, we're going to go to LQR. I don't know. Yeah, I can post the lecture notes, but I'm not sure how much you probably can follow. Yeah,
Okay.
we can certainly do that. Yeah. Yeah, LQR, it's kind of or LQG. You'll spend some time to explain, but when it comes to implement, it's just a couple line of code.
Oh,
yeah.
okay.
Right. So LQR essentially is the idea is similar like a pole placement, to come up with the gain matrix K, but the gain matrix K was calculated based on the optimal solution, right? And the previous to the pole placement, the K is based on what? A choice of the poles, right? Yeah. Yeah, designer's choice. So it's just basically, it's just a different ways coming up with the K, matrix there. Yeah. Okay.
Thanks.
Yeah. So anyway, maybe we'll stop early today. So then I'll talk a reduced order observer in the next lecture. Okay. Yeah.
Yeah.